determine so det now means determine, it's abbreviation with it. I'm going to use the day. Determine if 9 to the n plus n to the 4 over 8 to the n plus 5 to the n converges or diverges or diverge. Okay, so the theorem that allows us to answer this is the one I discussed at the end of Friday's class, and it was when I was running over time, so most people left. So if you haven't watched the video, then indeed you will be you don't know how to do this. But if you did watch the video, hopefully this stuff will seem reasonable. So what did we learn from that class? We learned that the only way a series actually converges is if the terms go down to 0. So theorem, if this series converges, then the limit of these guys go down to 0, which I asked you can think of as to think of the following metaphor, which just works in the case when we have positive terms an, that this thing represents doing an infinite sequence of steps. And if we do an infinite sequence of steps, the only way that's possible so that we end up in a finite place is if the step sizes go down to 0. That's not true if every now and again we take a step size of some non-trivial size, doesn't matter how infrequently. If we keep taking step sizes of some non-trivial size, we'll end up at infinity. Yeah? So no matter how small a step size, say 0.1, there has to be a point where we stop taking step sizes of size 0.1. Because if we don't, we continue to take step sizes of 0.01 forever, then we're going to end up at infinity. Yeah? It should be kind of reasonable to you. It should sound reasonable. Yeah? So this theorem, at least in the case when we have positive terms, makes sense to us. Yeah? So that gives us the divergence test, which is that if the limit of these things, these step sizes, is either not equal to 0 or doesn't exist, then the series cannot converge. Yeah. So what have we learned about series? We've learned that there are particular kinds of series we can actually calculate what they converge to, geometric series, telescoping series. And the only other stuff we've learned about series is whether or not they converge using this test, right? So a hint about what we need to do here is that it's asking us, does it converge or diverge? Yeah. So if it was asking us it could be that it's a series we can calculate the sum to, but then there's a good chance that it'll say, what does a series equal to, or what does it converge to? Yeah? So it's already giving us a hint that this thing is not a series we can actually calculate. Yeah? And it's more likely to be in this territory about answering whether or not it converges or diverges. And the only tool we have about that is this tool, is the divergence test. Yeah? You see what I mean? As always, please turn on the video unless you really don't want to, so I can get as much feedback as to what is making sense to you or not. All right, so does that make sense to you? Give me a thumbs up if yes, and do this gesture if no. Do this gesture if no. Okay, cool. Someone just somehow, there's an icon you can do that just gives me a thumbs up, and I don't have to see your video. So that's great. So yeah, please use whoever did that, however you did that, please share it on the chat so that other people can give me the icon thumbs up sign that I didn't know you could do. That's great. I wish I'd found that out before. Fantastic. All right. So there we go. There's a good chance we're going to have to use this test. So let's look at this sequence of terms. So If we look at these terms, so an in this case is a to the 9 plus n to the 4 over 8 to the n plus 5 to the n. Yeah, let's think about what are the dominant terms here, right? Let's simplify our life. As n gets bigger and bigger, look at the top. We have 9 to the n and then n to the 4. Which is the dominant term there? Which is growing faster, 9 to the n or n to the 4? Okay. Yeah. The point is that this guy here, this sequence, 9 to the n, is on the exponential function 9 to the x, right? So if we have f of x equals 9 to the x, right, then f of n equals 9 to the n, right? So the exponential function 9 to the n, right, is incredibly fast growing, right? It's even faster growing than e to the x because 9 is bigger than whatever, 2.711 or whatever, yeah? And this sequence is just points on this graph above the integers, right? That's how we, that's one of our tools to understand sequences, right? Is to find the graph that recovers the sequence, yeah? So this guy lives on this graph that blows up incredibly fast, whereas this guy, if we consider this guy, the function that recovers this guy is just x to the 4, right? And x to the 4 is not particularly fast growing compared to any exponential function, right? Because exponential functions kill polynomials, yeah? There's a whole different order of blow up of, maybe blow up's the wrong word, there's a whole different order of growth for the exponential function compared to polynomials. Polynomials grow fast, perhaps x to the 4, seems to grow very fast, but it is just totally massacred by the growth of an exponential function. So, I've gone on quite a bit about how it's really important to be familiar with these elementary functions. And that's all we're doing here, right? We're looking at this elementary function, g of x equals x to the 4, and this elementary function, just a version of the exponential function. Huh? Yeah? And what we have is that this exponential function is way, way, way above this guy right here. So the growth of this guy completely dominates the growth of this guy. For large n, we can basically forget about this n to the 4 because there's a tiny, tiny, tiny percentage difference compared to 9 to the n. Yeah? It's just negligible. We can barely notice it. You see what I mean? Yeah? Please use the icon. Is there an icon to show not thumbs up? Is there an icon that is like thumbs down? Just show me some icon that... There we go, good. So there's a thumbs down icon. Perfect. Oh, wonderful. All right, so we have that we can basically just think about the 9 to the n. So let's do this. This is not an equal sign. This is approximately equal to. So this is approximately equal 9 to the n, right? And if we look at the bottom, I don't like my 9 at all. If we look at the bottom, then we have 8 to the n and 5 to the n. Obviously, 8 to the n is the bigger term, right? Yeah? And they're both actually growing more or less at the same rate. They're both, they're both exponential functions. This guy's the bigger term. So let's just think about the 8 to the n. Yeah? So if we just had this, actually, no, let me write it like this because this is really true. These guys, this is really close to this for large n. Okay, this is really true. Yeah, because all we've done is drop this thing, which is negligible. So if we just look at this thing, right? 9 to the n is obviously bigger than 8 to the n. Yeah? Yeah? So this thing right here is bigger than or equal to 9 to the n over 2 times 8 to the n. Yeah? Which is a half of 9 over 8 to the n. Yeah? Which is blowing up. Yeah? So what we have is that this thing right here is blowing up more and more towards infinity. Yeah? So what we'd expect is that this thing cannot converge because not only are step sizes not going to 0, they're actually blowing up to infinity. Is that making sense? Yeah? Cool. Now, what we did was we did a kind of approximation to get a quick answer, right? We just simplified this as quickly as possible. Yeah? But this is almost certain to be valid because, again, And the simplification we made is such a small change. It's such a small change for large n to just drop this n to the 4. But if we want to be really make sure that we have the correct answer, then we don't make a simplification. We look more precisely. And if we look more precisely, what we notice that, in fact, we have that a to the n is bigger than equal to what happens if we just ignore the n to the 4, because it's just a positive term which just makes things bigger. So it's actually bigger than this thing, which, as we've seen, is bigger than 1 over 2, 9 over 8 to the n. So now there's no approximation. Now we have simply a true thing. So an goes to infinity, and series doesn't converge. Everybody with me here? Okay, what do? We looked at this and we tried to get a quick answer by just considering what the simplest version of this series is. We forgot the n to the 4. You would actually completely get the right answer just by forgetting about the 5 to the n as well, and just looking at 9 over 8 to the n. So the rule of thumb is when you have some series and it's division of something over something else, just consider the biggest term on the top and the bottom. Yeah? And that's going to give you a very good guide about what's going to happen. Yeah? So we got that it looked like it's going to infinity, and then we thought about it a bit more carefully. We found that these terms are bigger than something that actually is going off to infinity. Oh, so drop the n here. And that's all. Okay. We have this guy. And we have this guy. Oops, k equals n to infinity. Okay, all right, look at this. Let's start with the first guy. What do you think about the first guy? All right, so can you still see this somewhat? Yeah, okay. All right, so a series converges. K equals 1 to infinity. A series converges. Means the following. So if and only if the following, this Sn, which we define like this, the sum n equals 1 to capital N, an, this thing, as we range over capital N, forms a sequence. Yeah? So if and only if this thing, the partial sum, converges to some limit. If and only as this thing, which we define from summing the first n terms of this guy, converges to some limit. And that limit is what we call this thing. This thing has no meaning except as the limit of the partial sums, because we can't add anything together. We can't add an infinite number of terms, right? Nobody lives forever, right? So what possible meaning can we give to something like this? Well, the only meaning we can possibly give is that if we add n number of terms, where n is arbitrarily big, then that thing gets more and more consistently close to some particular answer. No? And And that's what this thing means. It means taking an increasingly large partial sum, because it's called partial because we're not summing the entire thing, and taking the limit as capital N goes to infinity. So this thing, the sum k equals 1, this is what it means. It's the limit as capital N goes to infinity of this thing. Oops. Okay. A series is a infinite collection of terms. In other words, it's what we get when we have a sequence and we add up all the terms. Yeah, so a sequence is just an infinite collection of terms put into a list. 1, 2, 3, 4, 5, up to infinity. A series is what happens when we try and add these things together. Add them all together, actually. Yeah? So that's what it means for a series to converge. A sequence converges. So let's call our sequence Bn if and only if the limit as n goes to infinity, Bn exists and equals L. And our picture for this is that if we take our x-axis and above every integer 1, 2, 3, 4, and so on, we put a dot that represents each element of our sequence. This is B1, this would be 2, so on. This could be B3, and so on. A series converges means that there is some number L, whatever it is, could be like this, such that if we put any thickness around L, for all sufficiently large n, all the elements of the sequence are trapped within this. That's what it means. Yeah? So we need this concept of a sequence to converge, or let me say that again. We need this concept of convergence of a sequence in order to define convergence of a series, because this thing as n is a sequence. Yeah? So we have to build this concept of convergence of a series out of the concept of convergence of a sequence. Yeah? So if you're new to this, then indeed these might seem difficult concepts, but it's just like anything. You will get more and more comfortable with this as we go along. Is it somewhat making sense? Yeah? People with video off, give me the icon. Give me the icon, people. All right, cool. All right, so let's look at this guy. This guy, if we look at these terms, so an is minus 4 to the e to the power k, like this. Let me say that, minus 4 over e to the power k. That produces this thing. And then if we sum n equals, let's be consistent. Let's call it ak. If we sum k equals 1 to infinity, then it gives us exactly that. Yeah? Yeah? But if we look at this term, so let's call this thing star star. But if we look at this thing, then the absolute value of these terms, right, is just 4 over e to the k. Yeah? So since 4 is bigger than e, which is 2.71 something, 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 so the limit as k goes to infinity of the absolute value of ak is infinity, yeah? So there's no way that the sequence ak is going to 0, because the limit of the absolute value is actually infinity. And that's actually oscillating up and down, up and down, up and down, further and further. Yeah, so the limit as n goes to infinity of an is not equal to 0, so diverges. Yeah? Everybody with me? Give me the icon. So, let's look at this guy. Let's look at this guy. Let's call this one star. So, if we look at these terms, let's rewrite this slightly. So, star is equal to the sum k equals 1 to infinity of 4 to the k plus minus 3 to the k over 6 to the k. Yeah? We're just writing 2 to the 2 as 4. Yeah? Okay, look at this. Do you think it converges or diverges? Well, let's take a look. If we look at the numerator, right, what is it? It's 4 to the k plus minus 3 to the k. Yeah? And the denominator is 6 to the k. So which of the numerator or denominator is bigger for large k? Denominator is bigger, a lot bigger, right? So, in fact, if we look at these terms here, I mean, this series would be less than what we would get if we had 4 to the k plus 4 to the k over 6 to the k. Yeah? Which would be the same as 2 times 4 to the k over 6 to the k. Yeah? Which would be the same as 2 times 4 over 6 to the power k. Yeah? And that would just be a geometric series, because 4 over 6 is just 2 over 3, which is less than 1. Yeah? So that should give us some anticipation that, or some intuition that this thing is actually going to converge. Yeah? But what makes it complicated is that we don't just have 4 to the k over 6 to the k, we have this terrible thing next to it. Yeah? So is there anything we learned that will help us understand this, given that we think it's going to converge? Perfect. This is the same as this, right? As 4 to the k over 6 to the k plus minus 3 to the k over 6 to the k. Just doing algebra, right? Yeah. And if we look at each one of these guys individually, then we believe it converges, because again, this is just 2 over 3 to the k. It's just a geometric series. This is just minus a half to the k. Yeah, another geometric series. So what we're doing here is we're summing the terms of two series, both of which converge. Yeah. And what are we allowed to do when we have something like this, where we're summing the terms of two series, both of which converge? Right. All the algebraic things that are true for finite sums are true for series whenever they converge. So one of the things we learned on Friday was that if we have the sum from k equals 1 to infinity ak plus bk, that's the same as the sum k equals 1 to infinity ak plus the sum k equals 1 to infinity bk. Oh, by the way, put in here in this chat so I see how many of you there are. Yeah? And that's what we're going to use right here, because we have that, if we let AK be 4 over 6 to the k, in other words, 2 over 3 to the k, and BK be minus a half to the k, yeah? Both of those series converges, so we can break this sum into this sum, the sum k equals 1 to infinity, and now let's write this as 2 over 3 to the k, and then let's write this thing as the sum k equals 1 to infinity of minus a half to the k. And now we're very happy, because now we're exactly looking at a geometric series, yeah? Or two geometric series. Yeah? So we just use the formula, right? So the formula is when we sum from k equals 0, so we're going to factor out a 2 over 3, and it's a 1 over 1 minus 2 over 3. Okay, the simplest version of the formula, the one I care that you can work out, is this. And again, let's factor out this minus a half. We have 1 over 1 minus a half, so it's 1 plus a half, like this, just from the formula for geometric series. Yeah? Give me a thumbs up or an icon if you're still with me here. Okay. Okay, thank you. Let's look at this. So recall that this is the basic form of the geometric series that we talked about. Yeah? When R is some number between minus 1 and 1. Yeah? When we sum from 0 to infinity. Yeah? And we have a little argument, and I strongly recommend you go over the argument and then figure out, and then learn how to recover this formula for yourself, because then you'll believe it, then you'll trust it, then you'll feel comfortable. Yeah? We have a little argument that this is exactly the same as this. Yeah? That's what we learned. And then from this, we can get any other thing, no matter what we start from, it can just reduce us to this by factoring out, right? So in this case, we start with k equals 1. So let's just factor out a 2 over 3, and then we'll have the sum from k equals 0 of this thing. So let me put this in a red box and write it elsewhere. So look at this. So the stuff in the red box is like 2 over 3, the sum from k equals 0 to infinity, 2 over 3 to the k. Going over the stuff here. Do you see what I mean? Yeah? And then it's 2 over 3, and then we just use the formula 1 over 1 minus 2 over 3. Yeah? Which gives us this. Yeah? And the same for this. We're just going to pull out a minus a half, and then we'll have this case when we start from k equals 0, and then we apply the formula. We have 1 over 1 minus a half, which is the same as 1 over 1 plus a half. Perfect. Thank you for the question. All right, and then we just, do the numbers, right? So 2 over 3. Oh, it just says, does it not just say, does it converge or not converge? If it says just, does it converge or not converge, there's no need to do the calculation, but okay, we're nearly there. So what is this? This is 1 over 3. And then this is 1 over, this will be 3 over 2. Yeah. So what's that going to be? That's going to be the same as 2, because 1 over 3 is 3, and that's going to be minus a half times 2 over 3. So that's going to be minus a half times 2 over 3. So that's going to be it's going to be 2 minus a third, which will be what? So it's going to be 6 over 3 minus 1 over 3, which will be 5 over 3, right? And that's the answer. Everybody with me? Okay, cool. Let's look at this one. Let's call this one star, star, star. What are your thoughts on this one? Secured by this thing. So this guy, a sum from k equals 1 to infinity, arc 10 of k plus 1 minus arc 10 of k, like this. Not k, yeah, I miswrote it. So it's from k equals n, like this. It's definitely a geometric series. It might be a telescoping series, or it might simply fail to converge. What do you think? If you look at these terms here, do you think that these terms are going down to 0? So let's visualize what arctan looks like. Arctan, another elementary function you've got to be familiar with at this point, looks like this, right? So if we look at these terms here, as k goes to infinity, does it look like these terms are going down to 0? Visualize them on the graph. So here might be k, and this is the guy next to it, k plus 1. Yeah? Yeah? So are these terms going down to 0? Indeed they are. Yeah, just look at the picture. So right here is arctan of k, and right here is arctan of k plus 1, right? And they're very close together, yeah? You can just see it. And the further we go to the right, the closer together they are, right? Arctan is increasing, but increasingly slowly because it's bounded above, right? Stops at pi over 2. You see what I mean? Yeah? Give me the icon or the thumb. Okay, good. So we can't just answer this by using the divergence test. These terms are going to 0. So that's the hint that it has to be something to do with telescoping series, because it's not a geometric series. We can't answer the question with the divergence test. Yeah? So it looks like the only thing that is relevant that we've learned about is the telescoping series. Yeah? And the telescoping series works because when we write out the partial sums, the sum from k equals 1 to n or whatever, then when we do that for something like this, we see a massive amount of cancellation. Yeah? And another hint that that's going to happen is the fact that we have this term and then the guy before it with a minus sign, which is the kind of thing what happened when we considered this. So when we had this thing, it was something like this. It was 1 over n plus 1 minus 1 over n, right? So it was, or maybe the other way around. It might have been like this. So it was this guy minus the guy next to it. Yeah? So when you see some kind of structure like this, it's a good hint that there's a telescoping series kind of thing going on here. So we're going to write out the partial sums, and then we're going to see what happens. So we call Sn. For some reason it starts at little n, but we're going to continue to do that. I think they're just trying to confuse you. It's not going to make much difference, but we start at little n. So we're going to sum from k equals little n all the way up to capital N of this stuff. Arctan of k plus 1 minus arctan of k. Yeah? And then we break up the sum. So that's the sum from k equals n to capital N of arctan of k plus 1 minus the sum from k equals n to capital N of arctan of k. And sure enough, we see a whole bunch of cancellations. If we start to write out these terms, what's the first term on this thing? It's going to be arctan of n plus 1. And the next one will be arctan of n plus 2, dot, 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 all the way up to arctan of capital N plus 1. Right? That is what's happening when we write out this thing here in the red box. Yeah? The red box turns into this. Yeah? And if we write out the other thing, let's call it, make it blue. If we write out this thing, oops. So we'll have minus everything in the blue box, and the stuff in the blue box will be this. We start off with k equals n, so we're going to have arctan of n, and then the next term will be n plus 1, and so on and so on and so on. Arctan of n plus 1 plus dot 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 dot, and the last term will be arctan of capital N. Yeah? So this stuff here is this stuff here. Everybody with me? Okay, look what happens. So the arctan n plus 1 gets killed by this arctan n plus 1. Okay? So this is killed by this. Yeah? The next term will be arctan n plus 2, will be killed by the next term over here. Yeah? In fact, every term on this, inside this red box, will be killed by one of the terms in the blue box, except this final term. That's the only survivor. That's the only thing that survives being killed by stuff in the blue box. Yeah, because every other term, we have a negative of it inside the red box. You see what I mean? Give me the icon or the thumb. So, what do we have from this total massacre of terms? The only survivors, again, are this guy. So we have arctan of capital N plus 1. And the only thing that is remaining from this thing, which is not being used to kill stuff in the red box, is the first term. The first term isn't being used, right? All these other terms to the right of the first term are used to kill stuff in the red box, but not the first term. So that is the only thing left of n like this. Are you with me here? Icon or thumb? Don't need to do both, but do one or the other. Some people are not giving any feedback. Maybe you're not watching for this particular question. All right, so that is the partial sum. And we know what convergence of this series means. It means the partial sums tend to some answer. This is the partial sum, right? Yeah. And we're taking the limit of this expression. The limit with respect to what? The limit with respect to what? No, take a look at the expression again. The limit with respect to what? Well, I guess now it's clear because there's only one other thing. Yeah. So Sn is the sum of all the terms from little n to capital N. And capital N, start again. S of capital N is all the terms from little n to capital N. Yeah. And to let this thing get towards this thing, we have to take capital N towards infinity. Yeah. Because this is the sum from little n to infinity, so that thing only has meaning if we have a limit from little n to capital N, where capital N goes to infinity and we tend to some answer. See what I mean? Yeah? Cool. So the limit as capital N goes to infinity is the thing that we're trying to understand. Call this thing star. So star equals the limit as capital N goes to infinity of this expression, arctan of n plus 1 minus arctan of little n. Yeah? And what's that? What's this expression? What's the limit here? No? Not quite. What part is giving us the pi over 2? The first part, right? But that's not the only thing, right? So we're asking for the limit as n goes to infinity of this expression right here. Yeah? So what's the limit? Yeah. So the answer is pi over 2 minus arctan of little n, like this. Because as capital N goes to infinity, this doesn't change at all. So little n was just fixed in the problem right here. For some reason, we have little n is where the number where we start, right? Yeah? And little n is any number they've pre-chosen. It could have been 7, could have been 164, whatever. Yeah? But depending on what little n is, we get a different answer in the limit. Yeah? And that is part of the answer. For different little n, we get a different answer. And that is what happens when we take the limit with capital N, because little n is just not affected by taking the limit. This is just a constant sequence with respect to capital N. You see what I mean? Yeah? Give me the thumbs up or leave me the icon. Cool. All right. Looks like most of you are with me here. So let's recap. We understood this one very quickly because we see that these terms are blowing off either to minus or positive infinity. The absolute value is blowing up. Yeah. This guy, we had to think a little bit, but when we rewrote it as 4 to the k plus minus 3 to the k over 6 to the k, and we just broke that up, we saw it's the sum of two series, yeah, both of which converge. So we just wrote them separately, found the answer, and that was it. Yeah, that was not too bad. This guy we had to think a little bit, yeah. And by process of exclusion, it's not a geometric series. These terms are tending to 0. Yeah. So the last relevant thing that gives us a chance to answer this question is if it's a telescoping series. And the second hint is that we have, let's put it over here, let's look over here, it looks better. We have this guy minus guy before it, yeah, which is the kind of thing that happens when we look at telescoping series, because there has to be some massive cancellation. Yeah. So when it's a telescoping series, we write out a partial sum. We write it out carefully. Yeah. And then we just see all the cancellations that happen. There's a massive amount of cancellations. Only two terms survive, this term and this term. Yeah. We remember that the limit is as capital N goes to infinity, so then it's just finding the limit of this thing, which you can do, right? Because if it's the limit of this thing, you know, and this thing is just a constant. It's not changing with respect to capital N. Yeah. Cool. All right. So we can do these things. Huh? We can do these things. All right. Shall I do another series question, or do you want anything? Do you want a different thing? The series was AK is k minus 1 factorial over k factorial. Is that correct? Is that right? Okay, good. So does this converge? Okay, let's look at this. So If we look at k minus 1 factorial, it is k minus 1 times k minus 2, dot, 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 dot. The last term is 1, right? And k factorial is k times k minus 1, k minus 2, dot, 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 times 1, yeah? So if we just consider the quotient of this, k minus 1 factorial over k factorial, then we have k minus 1, k minus 2, dot, 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 1, and on the bottom we have k minus 1, k minus 2, dot, 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 dot. And we see a whole bunch of cancellations. We see that k minus 1, k minus 2, and so on. All these guys will cancel, and the only thing left is just 1 over k. Yeah? Cool. And then if we just look at this, then 1 over k, we see what happens. At 1, it's 1. At 2, it's 1 over 2. At 3, it's 1 over 3. This thing is definitely converging down to 0, yeah? So it might look complicated because the k factorial, it's kind of a complicated expression perhaps, but this case it just simplifies rather quickly. Yeah? Is that okay? Do you want me to do another k factorial question? Well, give me an example. Okay, so it's going to be something similar, right? So let's look at this. Okay, we're going to keep the 6 minus n factorial like this, and let's write out what 6n plus 1 factorial is. So it's 6n plus 1 times 6n itself. Just write that without brackets. 6n itself, and then 6n minus 1, and then 6n minus 2, and so on. Yeah? All the way down to 1. Yeah? If we look at this, then we see that from here onwards, yeah, in the red box, what we have is actually 6n minus 1 factorial. Yeah? You see what I mean? Okay, so we can write this as 6n minus 1 factorial over 6n plus 1 times 6n, and then 6n minus 1 factorial. And then the 6n minus 1 factorials cancel, and we just have 1 over 6n plus 1, 6n. Okay, and then this thing just goes to 0 for the same reasons as before. Yeah? So the limit as n goes to infinity. Right. So since it was like a bit slow starting because of difficulty finding the practice problems, so I can read them. I will take one more question if you got it. Do you have any final question?